right, so, the enzyme, the ATP synthase it's membrane bound and has the I guess it should be a little more like that. Right, so the top part was the membrane bound. F0, its job is to pump protons from high concentration to low concentration. So what we were looking at the other day was this F1 complex, where it had 3 different states it could be in. Open, tight, and loose. Okay, so the open spot, nothing is bound. In the tight spot is going to be where we release ATP, and then the loose is where the ADP and PI bind together. So if we work through how we get from ADP to ATP, first step, so really there are 3 subunits all working together to make the major complex. So the first thing that's going to happen is the ADP and PI bind to the loose subunit. The free energy from the proton gradient is going to drive the conversion of the loose subunit to convert into a tight subunit. It's going to involve a conformational change to all 3 subunits. So the loose subunit has now become the tight subunit. The tight subunit has now become the open subunit, and the open subunit has now become the loose. So they've all shifted by 1 spot. So if this is step 1 where something is bound, I draw the same over here. So the exact same, you're still looking at the exact same.
They go counterclockwise? If there is counterclockwise?
Yeah, that's counterclockwise, yep. So what was loose is now tight. What was tight is now open. What was open is now loose. So we're ready to bind another one and release another one. So then the only way we can do this binding and releasing is this proton gradient provides free energy for the conformational change of the F1 subunits. So F0 is actually rotating to kind of store up energy, and that stored energy can then be released by the conformational change. So if you imagine like you're holding onto the bottom part of and there's like a spring in between the top and the bottom, and you wind up the spring. If you release your bottom hand, it spins. Same kind of thing. So the top part is spinning, and you're building up some free energy that then the bottom part can use to rotate and change its conformation. If that's an easy picture to kind of think about. Any questions on ATP synthase? It's pretty neat. It's a pretty neat little thing. Little enzyme. Yeah, so F0's job is to pump the protons, and F1 has the 3 subunits that, as their net result, makes ATP.
What do you mean, like the F1, is it a,
It's a protein, right? So the whole thing is an enzyme.
ATP
And-
synthesis?
Yeah,
Okay.
so the whole thing is ATP synthase that has 2 parts to it. They can't really be subunits. Maybe you could call them subunits. F0 and F1 are subunits of the whole thing, but then F1 has subunits within itself.
And so the subunits of F1 are the LO and T?
Yes. Yep. I'm sure they have fancier names, but that's what we call them. All right, in that case, let's look at I didn't bring my slides down here today. I have no idea where they are, so I'm just gonna. I have this, so we're gonna look at this last one, control of oxidation phosphorylation. So the picture, the picture's in your textbook, so I wasn't gonna spend a lot of time looking at the textbook. It's just, this is the whole scheme, starting glycolysis, going through citric acid cycle and all the different activators and inhibitors. But I want to more specifically talk about control of oxidative phosphorylation.
How fast is ATP synthesis?
How fast is it?
How fast?
I don't know off the top of my head. Pretty fast, I imagine. Because you figure if you're able to go through all glycolysis and citric acid cycle in a few seconds, then that last little step must just be like really quick to make the ATP. All right, so control of oxidative phosphorylation. right, so for every one glucose that enters glycolysis and heads through the citric acid cycle, we get 10 molecules of NADH, which will then be sent through the electron transport chain. The NADH are not sent through, the electrons stored by the NADH. So returning the NADH back to NAD plus releases those electrons, and those electrons can then travel through the electron transport chain to pump protons to provide energy to make the ATP. So in both the citric acid cycle and glycolysis, there are going to be enzymes that control NADH production, right? They've used NAD plus as a cofactor, and so if those enzymes are operating, then they're going to make NADH, which then provides the electrons to make the ATP. So besides all the other ways we have to control, like PFK and all those enzymes, ATP concentration also controls these enzymes that use NAD plus to make NADH. So, like, for example, these are just a few. Right, so malate dehydrogenase is an enzyme that uses NAD plus to make NADH. So isocitrate dehydrogenase. Right, so those are just some examples. So all those, right, citric acid cycle enzymes and glycolysis enzymes that use NAD plus to make NADH can be controlled by what the ATP concentration is to forward it through the cycle. All right. Questions about that? I need to put down my pens. That was very exciting for a second there. All right. In that case, these are some thought questions we're going to work through. I know, very exciting. We won't get through all of them. So we have a separate piece of paper. All right, so looking at the electron transport chain, what are the molecules that are needed to transport electrons? We need to use NADH. There should be at least 3 more. Yep, we use some FADH2. CoQ. Two more. Cytochrome C. Iron sulfur clusters. All right, so we need 5 cofactors in our electron transport chain to be able to transfer electrons from complex 1 to 4 or from complex 2 to 4. I'm just restating what I was just said. No question. Yet, very excited. Okay. Okay, which of these cofactors carry electrons but do not change their protonation state? Should be pretty obvious considering I put it with the protons. So which of these carry electrons only? Cytochrome C. Yeah. How are they able to carry electrons only? What happens to them? Right, they just change oxidation states. So both cytochrome C and iron sulfur clusters both contain iron. One's more obviously, they just go from +2 to 3. So they don't change protonation state.
They do not.
Right, they don't carry protons, they just change the oxidation state of the iron. Okay, I'm going to skip that question. We'll go down here. All right, so everybody should sketch a little diagram that looks like this. Complex 1, 2, 3, 4. Okay, so here's my picture of, really big picture of 1, 2, 3, 4. Let's come back to that. All right. So the first question is, how do we know which side is the matrix and which side is the intermembrane space? Is where all the... Okay, so is the matrix going to be on the top or on the bottom? On my snazzy little picture here. So the question, so complex 2, right, is succinate dehydrogenase. That is on the matrix side. So this side has to be matrix. And why do we know that succinate dehydrogenase has to be on the matrix side? The citric acid cycle is in the matrix. So if complex 2 is part of the citric acid cycle, then it has to be on the matrix side. Good thought deduction there. Okay, so we have our inner membrane space. Good. So you might have to go back and look at one of your other diagrams, but where could I find coenzyme Q? What complexes need Q? All right, so those are two places that coenzyme Q occurs. Where are the other two coenzyme Qs going to be found? Because there's 4 spots altogether. What's the other complex that needs Q? 3. And how many Qs does complex 3 need? It needs 2. Four spots. This one, I'm showing it all together as once, but it really should be 2 loops to make that Q cycle. All right, what complexes contain cytochrome C? 2. Actually, 3. You meant 3. Okay, so cytochrome C is going to be found in complex. Cytochrome C. How many cytochrome Cs, or cytochromes in general, are in complex 3? You have to go back and look if you don't know. There are 4. Well, yeah, so there are. I don't have my sheets, but if you were going to go back and look, there is a cytochrome C, a cytochrome B, and then down here we have all right, as part of this Q cycle, we go from B to C, and there's a C over here on the matrix side. Cytochrome C?
It's a cytochrome C.
Right, so there should be cytochrome C, B, and then C down here.
C to C.
It should be C to C, so it's 3 plus to 2 plus. It's just being oxidized. It is, right, so if you go back and look at the Q cycle, it's the one that's sending electrons back into the membrane. Yep, so if I flip back here. Yeah, it's just one of the cytochromes on the inside. Oh, I got my cytochrome 3, 2 on the wrong side. Sorry, guys. My picture's upside down. Cross that out, put those on up here. Should be on the inner membrane space side. That's from 3 to 2. 3 to 2, I just put it on the wrong side. It should be on the inner membrane space side. I put my cytochrome C on the matrix side instead of on the side of inner membrane space side. All right, so which of these things that we've just talked about have heme groups? All the cytochrome C should have heme groups. Yep. So you can just put that as a note someplace. So heme groups are all in the cytochrome C's and B's. Cytochrome has heme. Which complexes would have iron sulfur clusters? Yep. Let's see here. Which complexes need NAD? And is the NAD, where's the NAD coming from? The matrix. And why is it coming from the matrix? Same thing. It's coming from the citric acid cycle. So I got to put my NADH. Okay. Which complex needs FAD? H2. 2. And where's the FADH2 coming from? Matrix or the inner membrane space? Matrix again. All right, so then finally, we've pretty well covered complex 1, 2, and 3. What do I need complex 4 to do? What's its purpose? To make the water. Yep. All right, so oxygen and 4 protons make 2 waters. No, it should be on the matrix side. Yep. Yeah, it's going to pump 4 and then use 4. 4 protons to make 2 waters. Okay, last question on this. Which of these complexes pump protons? 1, 3, 4. Okay, 2 is the only one that doesn't pump protons. It transfers electrons, but no pumping. So they all pump into the air membrane space. So is that the high concentration or low concentration? Excellent. So then if I was to draw complex 5, which is the ATP synthase, which way would it be pumping protons? Inner membrane space to matrix or matrix to inner membrane space? Yeah. It's going to pump from high to low. I know what you're saying. This way, this way. Which way, I guess, of these, which one should have the lowest redox potential? 1, 2, 3, or 4? 1. Which one has to have the highest oxidation potential? The last one. Why is that? We go low to high. So we pump into the high, but then we go low voltage to high voltage. So 1 has the lowest potential, and 4 should have the highest potential. Because for the electrons to flow, they have to go from low voltage to high voltage. Questions on our electron transport cycle, chain? All right. In that case, in the last 10-ish minutes of class, why don't we take a group quiz and then you turn some questions for me to answer. Friday.
We say that every time.
Oh, yeah, we got it.
Don't forget, homework's due Friday. So, can I just have class on Friday? I do. The last home day on not me.
Yeah.